All right, here's your second question for the office hours on May 12th. Go ahead and pause the video, give yourself 15 minutes to work through this, then come back for your answers. So this is a problem that walks you through different types of molecules and explains their physical properties. We have NH3 first. If you want to identify molecular force, intermolecular forces, always draw it first. So I'm going to draw my NH3 molecule. If it's on the test this year, you probably wouldn't have to draw it on the test, but you might have to refer to its shape. So having a scratch piece of paper is a great idea on the test. So I sketch it and I identify the intermolecular force type here is hydrogen bond. And it's hydrogen bonding because we have nitrogen, oxygen, or fluorine attached to hydrogen. In this case, we have nitrogen. And it has to be attached to the hydrogen, so we get a really positive hydrogen and a really negative nitrogen, so we can hydrogen bond there. In it, F3 looks like this. Now this can't hydrogen bond because there's no hydrogen. So what do we look at here? This is a polar molecule. It's your trigonopyramidal shape. So it's got kind of that tetrahedral structure, but we have a lone pair of electrons on the top, and that makes this polar. So this is a dipole-dipole, and that's what you should say for part I. And then if we want to account for the difference in boiling points, how do we do that? Well, the first thing you want to do is recognize who has a higher boiling point. In this case, it's our NH3. Now, there's two things that impact boiling point. It's the mass, or the size of the molecule, and the size of the molecule depends on, or impacts its ability to be polarized. And in this case, our molecules are very similar in size in the structural shape. The mass of our NF3 would be higher because fluorine has a higher mass than hydrogen. So just simply based on the shape of it, you have bigger electron clouds on your fluorines, we would say NF3 is a higher boiling point. But that's not the case. So there must be something else impacting it. And the main thing impacting it is your strength of intermolecular force. So our hydrogen bond is a really strong intermolecular force, and dipole-dipole is weaker. And so the intermolecular forces of hydrogen bonding are holding them together, and it requires a higher temperature to boil your NH3 because it has a stronger IMF. And that would be your explanation. So let's read their answer key here. For part I, you'd get only 1 point for correctly identifying that you have hydrogen bonding and dipole-dipole. For part I, the higher boiling point in NH3 is due to greater strength of hydrogen bonding. You get 1 point for saying that. That's stronger than dipole-dipole. For our next part of the problem, it asks you to compare the melting point of KCl to the melting point of NaCl and identify the type of bonding in each substance. You should identify metal attached to nonmetal is an ionic bond, which is a transfer of electrons. Account for the difference in melting points, which one's higher again. It looks like our NaCl is a little bit higher, not by a lot, but it is a little bit higher. Why would that be the case? Well, you want to look at two things. You want to look at charge, +1, -1, +1, -1. That's the main determining factor. Our charges are the same here, so then you want to go to ion. Size. So we have sodium, and then we have potassium. Well, potassium's larger, sodium's smaller. The smaller the ions, the closer they can get together, and according to Coulomb's law, the closer two charges are, the stronger they attract, which require more energy to melt it, and that matches our data. This is the higher boiling point. So NaCl is melting point. NaCl is your answer, and your justification, smaller ion, allows them to be closer together. So let's look at their answer key here. For I, they're both ionic bonds. You get 1 point for that. And let's read their explanation here, because they type quite a bit. This year you'll be typing, and all this could be typed out. The difference in melting points is due to the difference in strengths of ionic bonding. The charges on the cations and anions are the same. It's important you say this. Don't just identify it in a problem. State this, because this is allowing you to move to the next most important thing, which is size of ions. So they're the same size. Therefore, the relative size of the ions is a determining factor. Since sodium is smaller than potassium, the lattice energy of sodium is higher than potassium. Thus, more energy is required to overcome the forces. And you could even help this a little bit more by connecting it to Coulomb's law and saying Coulomb's law, the closer charges are together, the stronger they attract. Therefore, lattice energy will be higher in sodium chloride. So you get 1 point for that. Our next part, you get a list of ionization energies. And there's a trend here. It's increasing. So as you go down, it increases here. For each of the three elements, identify the quantum level. This is the shell of electrons for the valence electrons in the atom. Well, just go to your table, and this is your first shell, second shell, third shell, and we're in that third row here. Here's our elements that we're considering. Oh, not sulfur, silicon here. So this is our third shell, so you should have just said third shell electrons. And then for part II, explain the reason for the trend. Why does it increase as you go this direction off on your periodic table? It's harder to take the electron from phosphorus. It's harder to take the electron from chlorine for your first ionization energy. How do we do that? Why did they skip sulfur, by the way? You could look back at an old video that we talked about those paired electrons in that p orbital. So we skip sulfur here. So silicon, phosphorus, and chlorine. Let's look at their structures. The short answer is effective nuclear charge increases as you go this direction. Let's look at what that is, though, for those that don't remember. This is your effective nuclear charge. So here's our structures for our atoms. And let's just look at I'm going to write this in each shell. Look at our structure. So silicon has 2 electrons in that first shell. It has 8 electrons in the second shell. That's our 1s2. And this would be the 2s and 2p combined. And the 2s holds 2 and the 2p holds 6. So we get 8 electrons. And then in that outermost shell, how many do we have? 1, 2, 3, 4. So this would be the 4 electrons in that third shell. How many shielding electrons do we have? We have 10 shielding electrons total. And inside my nucleus for silicon, how many protons do I have? Let's find it. 14 protons. So we get 14 positives in the middle here. And effective nuclear charge on that outermost electron, we have to remove 1 electron on the outside. Effective nuclear charge has this little symbol here. And it's the total charge on the inside minus your shielding electrons. In this case, we have 10. And so I get effective nuclear charge of 4. And your effective nuclear charge will match the charge on your table. So this column is always plus 4, plus 5, plus 6, plus 7, plus 8. But this is how you calculate it. So if you had to justify that. Let's go to phosphorus. We have 2 electrons in our first shell. We still have 8 in our second shell. But now we have 5 in our third shell. And inside for phosphorus, again, you go to your periodic table, find your number of protons. It's 15 now. And we can calculate our effective nuclear charge here. And so effective nuclear charge for this one would be 15 minus 10 still, 10 shielding electrons. So we get plus 5 now. That's a stronger attractive force for the outside electron. It's effectively attracted to 5 protons on the inside. And if you do that for chlorine, you'll get an effective nuclear charge of 7. Plus 7. So it's a stronger attraction. So if you're explaining it, you could explain the attractive force for the outside electron increases as you go to the right because there's more protons added to the nucleus, and the number of shielding electrons remains the same. So we still have 8 and 2 and 8 and 2, and this would also have 8 and 2. So we're adding more protons, but we're not changing the number of electrons that are shielding it. Therefore, the outside electrons get a stronger attractive force. And let's look at their answer key. 1 point for saying the third level for part I. And then here's their explanation. Because the valence electrons in all 3 elements are shielded by the same number of inner core electrons, and the nuclear charge increases going from silicon, phosphorus to chlorine, or you could say number of protons attractium increases, anything would work for that. The valence electrons don't increase in attraction to the nucleus. And valence electrons having greater attraction will be more difficult to remove and require higher ionization energy. And that's your explanation for 1 point. Okay, our next part here, D. A certain element has 2 stable isotopes. The mass of isotope 1 is given, the mass of isotope 2 is given. Identify the element. How do we do this? Well, if there's only 2 isotopes, that means the mass of our element has to lie between these 2 masses. So it has to be above 62.9, but below 64.9. So let's look at our table. Where's our 60s? Well, it happens right about here, 62.58. So it's going to be copper right here. This is the only element with masses between those 2 isotopes. So that's your justification for I. It's copper because the mass lies between the 2 masses of the isotopes. Which isotope is more abundant? Well, whichever isotope is closer to the actual mass of the element. So 63.5, which is closer to 63.5? Is it 62.9 or is it 64.9? Well, the answer is 62.9 is closer to my actual mass. Therefore, this must be in greater abundance. And you remember in class when we had to calculate average atomic masses, you had to do that by a weighted average. And that just means that this particular isotope has more impact on the actual average atomic mass than this isotope because there's just more of it. It's more abundant. And so your answers, I get your points here, 1 point for choosing copper and justifying it, and then 1 point for choosing 62.9 because it's closer to your actual mass. That's your justification. So if you add up your total points there, if you beat 3.9 out of 8, then you're beating the average. So good job on that. I hope that helps, and good luck on your test this week.